in the previous lesson, we were come to this topic, which is the three families of biomass energy conversion, and we have a general look to the three families: thermochemical processes, biological processes, and mechanical processes. And we started to consider the thermochemical processes, which are possible into three different treatments: combustion, gasification, and pyrolysis. Then we moved to the focus of these processes, and we started to talk about the combustion process, which usually has an equivalent ratio more than one. So we give to the system more air than the stoichiometric needs in order to have a perfect combustion. These are the final products: carbon dioxide, steam, and ashes, and of course energy, because the main goal is to produce energy that we can convert into heat, steam, electricity, also refrigerated water, and so on. We just have seen this slide, where you can see the main combustion reaction. Of course, we have three main elements: carbon, hydrogen, and oxygen. And so the final products are carbon dioxide, water, but also other products, for example, nitrogen, sulfur, chlorine, that produce, in some cases, pollutants, for example, nitrogen oxides, sulfur oxides, or compost with chlorine. These are the three stages we have in every kind of combustion, from the small size to the very large scale, which is the first stage is a drying, because when the temperature inside our system goes up to 100 degrees centigrade, we start to have the water evaporation, and so this is the first stage. The second stage is always something like pyrolysis, because you have to imagine the biomass with a volume, and so inside the biomass we start to have high temperature, from 300 degrees to 500 degrees. So high temperature without oxygen, because inside the biomass you can have oxygen. And so the process is a pyrolysis, so a degradation of biomass into a solid char, or a liquid compound, which is called tar. And then the final stage is the oxidation, the combustion. The combustion that starts from the surface, where we have biomass, oxygen, and high temperature, and then goes up to the internal part. So every combustion has always these three stages. Okay? And this is another way to see the combustion, starting from the composition of biomass, carbon, hydrogen, and oxygen mainly. Okay, and of course nitrogen, sulfur, metals, and so on. Then we have the first stage, which is the drying, when we are over 100 degrees. And here you can see primary air, because the first part of the combustion is allowed by using primary air. Here we have the pyrolysis inside the biomass, and then with the secondary air, so more air, we have the complete oxidation of all the products. Okay? You have energy, heat, that you can convert into every form of energy you need, ashes, of course, and other combustion products. Okay, now we will have a look to the typologies of biomass plants, starting for the small one to the biggest one, which are, for example, a cogeneration plant, so combined production of heat and electricity, and also up to the district heating, which is a very large plant that distributes heat to towns, to cities, and so on. So, yes, I can jump some slides. So, these are the biofuels we have just introduced in the first lesson. The most, maybe all the possible biofuels you can use in a boiler or in a heating system. Yes, we have just seen pellet in the last lesson. Wood chips here. Briquettes, which is another way to use sawdust, and of course wood for residential uses. These are the biofuels that we can use, but of course the pellet, briquettes, and wood are used mainly in residential case. When you move to big plants and to industrial energy production, the only used biofuel is wood chips. Because, of course, mainly the cost, pellet or wood have a cost twice, maybe 4 times the cost of chips. And so, of course, if you move to big plants, to industrial plants, you have to use only wood chips. Okay? These are the 1, 2, 3 are the plants we will see in the next slides, and in this graphic you can see that we start from very small plant, for example the pellet system for a small house, up to very big plants. Here you can see the kilowatt, maybe megawatt. We can reach. We can also go over 10 megawatts plants. So there are plants also 20, 30, 40 megawatts of energy production. This is the simplest example of bioenergy plant, which is a system for houses, but it's only something's beautiful, but not so efficient for energy production because its efficiency is very, very low, only 20%. Of course, we can move towards a pellet system, which has a higher efficiency. Up to, yes, boiler systems. Boiler system uses biomass to heat a thermodynamic fluid, for example water, of course, for domestic heating. So this system, like a methane boiler, you heat water, and the water reaches all the system for the distribution of heat. Okay, this is a wood boiler, but we have also, we have also pellet boilers without or with a system that where you can put pellet for some days autonomy. Up to these are still pellet system, where you can see also we can start to see also the transport systems, which is very important for solid biofuels, but in general for solid fuels. A very important difference with traditional methane boiler is that you have methane directly into pipeline that reach directly the boiler. So you then to consider the transport and the distribution of the fuel. In the biofuel system in general, the design of the transport, storage and transport system is very important. It's very important, and you have also to consider some spaces where you can put biomass to have storage. I move directly to wood boilers, which is the, as I said you, the most used system, starting from the domestic use up to the industrial use. This is a typical design of a biomass boiler system. Here you can see the boiler. Here a storage. Because another important difference with methane is that you have methane whenever you want and in every quantity you need, because actually the methane net reach every house. So you don't have to consider any design of this part. In biomass systems, you have to consider that you have to buy wood chips, and someone has to bring you the biomass when you need. So you have to design a storage with a correct autonomy, and the correct autonomy depends on the uses, if it's domestic, industrial, and so on. But you have to consider that at least 1 week, 2 weeks, 1 month, you have to have a volume that can allow an autonomy of at least this period, in order to have to organize the service of biomass usefully. So this is the storage, and after the storage, you have to design and to build a correct transport movement system in order to have an automatic system that from the storage collect biomass and move biomass in the correct quantity up to the boiler. And you are moving wood chips that are small chips with 2, 3, 4 centimeters length, and so you have to choose the correct movement system. For example, this is a screw used for move wood chips. So, for example, here there is another system that moves biomass to the screw, and then the screw moves biomass up to the charging system. Okay, and it's a very important part in order to avoid breakdown, to avoid stopping the system when you have some problems. Okay. And here you can see that the range of boilers start from 35 kilowatts. So you can start from domestic use if you have, of course, not a very small apartment, but if you have an house, you can think to use a biomass system up to 7 megawatt, but also, as I have said you, also 50 megawatts, also 60 megawatts. The efficiency is very high because we are very close to 90%. And here you can see two different biomass boiler systems. Fixed rate and moving rate, moving furnace. These are two different systems. The first one is mainly used for small plants. The second is used for higher biomass plants. The first one is a fixed rate. So the system here is the furnace, the boiler, where comes the biomass from this system, and here we have the primary air with the first combustion, and then, for example, here the secondary air that completes the oxidation also of volatile that still can burn. And then there is the heat exchanger that move heat from the exhausted gas to water that you can use for your needs. This is the simplest system. The second one is the moving rate, which is a very is used very often in higher, in bigger plants. Here you can see the movement system. So biomass comes from the storage, moves here. This is the boiler. So biomass comes here. Here there is a moving rate. So there is some like some stairs where biomass moves, goes down, and the combustion continues here. And at the end of the system, we have only ashes. Okay? So the combustion moves here, and here we have exhausted gas with secondary air. So primary air usually comes from here. You see some ventilators here. And secondary air complete the combustion of exhausted gas. So exhausted gas complete the combustion here and here, and then there are a pathway in order to transfer heat from exhausted gas to water, for example, water, but any other thermodynamic fluid we can use. In the next part of the lesson, we will see other thermodynamic fluids, for example, diathermic oil or other fluid used for industrial processes. Okay? So the exhausted gas transfer heat to water and then goes to atmosphere or to a treatment system for removing pollutants if necessary. Okay? Another picture of the system. And here in this very simple system, you can see, yes, the biomass boiler in a very simple way, and the distribution of the energy. If you want to produce heat for residential or for industrial use, you have a net for the distribution of the fluid with a pump, of course. The important thing here is this boiler, this boiler, because yes, another important difference between traditional methane boilers and biomass boiler is this boiler, this accumulation of hot water, for example. Because biomass boiler has a very low transition, initial and final transition stage. When you have to start to use the boiler, you need a time, for example 1 hour, to allow the boiler system reach the temperature for the correct combustion. In the methane boiler, this is a very low time period. In biomass, this period is higher, so you need a lot of time to reach the temperature in the boiler, and at the end of the production phase, you need a lot of time to goes down with temperature. Okay, and so into these transitory stages, you have to optimize the storage of energy, because, for example, when you start, you need some energy in the period when the boiler has to reach this temperature, and in the final stage, you have to avoid to lose energy, because if I don't need any more energy here, I switch off the boiler. But the boiler, for example, for 1 hour or 2 hours, has a temperature that produces energy, and so this boiler allow to don't lose this energy, because I store it into this boiler with hot water, and of course I can use it when the boiler restarts and needs a time to be productive. Okay, so it's this element, this component, is fundamental in every biomass system. It's okay, it's clear. It's the function of this system, and so you have to, of course, to design the correct volume in order to store during the transitory stages the heat. Yes, here you can see some storage. Of course, this is a very homemade storage. For pellet, I go very quickly here. Okay, this is an example useful to understand the every kind of storage. I repeat, from the residential use to the industrial use. How we can evaluate the volume, for example, in cubic meters, the volume we need to have an autonomy. For example, this is, I don't know if I have other example. No, okay. We can use this example. For example, you can think about a boiler. We can also make a difference between a boiler fed up by pellet and fed up by, for example, wood chips. Here you can see a pellet boiler, 20 kilowatts. Okay. So 20 kilowatts. You have to evaluate the yearly needs of energy. For example, you have this quantity of pellet you need in 1 year, 8,000 kilograms, 8 tons per year. Okay. So how we can evaluate the storage capacity? This calculation is to evaluate the volume you need for an autonomy of 1 year. So if in 1 year you need 8,000 kilograms, in order to evaluate the volume of this quantity, you have to divide it in the, what is this? This is the weight of pellet in 1 cubic meter. So if you have to evaluate the volume, the storage, the volume storage, what you have to consider that here you put pellet, for example, or wood chips here. And what is the occupied volume of pellet? It depends. For pellet, for example, this is 1 cubic meter. So 1 meter, 1 meter, and 1 meter. If you put pellet in this cubic meter and you complete the volume, for pellet you have 600 kilogram per cubic meter. So pellet here is 300 kilograms. For example, if you have the same storage of 1 cubic meter, and you put inside the wood chips, for example, so the alternative biofuel, which are very irregular chips, you usually have 250 kilograms per cubic meter for wood chips. So in 1 cubic meter you can put 250 kilograms of chips, and it depends on the form of the biofuel, because of course you have pellet or wood chips, but also some part where there is only air because of the storage of the system. And so these are the used values for these two systems. So if you divide the yearly need of pellet into the density of pellet, you obtain the yearly volume 13, maybe 15 cubic meter for 1 year. And now you have to, for example, choose the autonomy, which is not of course 1 year, but it depends. If you want an autonomy of 1 month, you divide 15 cubic meters into 12, and you obtain, for example, 1.5 cubic meter storage. Okay? And this is the general way to evaluate the storage of the system. The same for wood chips, but you have to divide not for 600 kilograms, but with 250 kilograms. And of course, you obtain approximately 32 cubic meter for 1 year. The other considerations are the same. These are some moving systems for pellet, in this case, for pellet with screw, with pneumatic systems. When you have chips, wood chips, the systems are only screw or similar systems. There are some possible configuration of storage and biomass boiler. Okay. Okay, we are moving towards bigger plants, so we are moving to industrial systems. Here are some examples of movement systems. This is the screw I just showed you. For example, other systems, for example, these are rakes that when the storage is full have this movement, and for example move wood chips toward this part. This is another system that moves wood chips, rotating system that have this movement and move biomass, for example, into this direction. And here there are, for example, a screw that move wood chips to the boiler system. Big size boiler. Here you can see a scheme I found as picture. We are in an industrial configuration, and so you have to organize the transport system with trucks, for example, that put to the boiler plant wood chips. For example, this is a weighing system to evaluate the quantity of biomass that the trucks transported. The chargement system, so you can see some configuration to the automatic system. So here you have to organize the transport. From there you have an automatic system, for example moving rails that move biomass into this direction, and this can be a screw that move the biomass up to the boiler. This is the boiler with the exchanger, the treatment of exhaust gas here. So, for example, we will have a look to the systems that collect pollutants before they go into the atmosphere. For example, cyclones or filters and so on. And in industrial system, you have usually obtain heat at high temperature, not 100 degrees or 80 degrees as in the domestic use, but you can also have 300 energy at 300 degrees, 400 degrees, in order to obtain, for example, electricity, for example, steam, for example, refrigerated water. So you can use this energy in different ways. This is, for example, a moving rate, the same we have seen in some slides, some slides ago. But yes, it's very big system in this case. But the working system is the same. It's not very clear, but this is the internal part of the combustion chamber in a moving grid. So these are the stairs where the biomass goes down, and it's difficult to see, but there are a lot of small holes where the primary air goes inside the system, and then the exhausted gas complete the combustion. This should be some hole for secondary air, and transfer heat to thermodynamic fluid. Other pictures of this plant. Other examples of biomass combustion systems. For example, it's a rotating boiler which rotates and creates a bed of biomass that complete the combustion during the movement inside the system. Fluidized bed, it's another system with a bed that moves with sands that complete the combustion and favorite the exchange of heat inside the system. Recirculating bed and so on. When you have biomass boiler with large size, you of course prefer to have a cogeneration, or maybe probably a three-generation system for the combined production of heat and power. Or in three-generation, you have the combined production of heat, power, and refrigerated water. And this kind of system, of course, guarantees a high efficiency in the system, because, for example, if you produce only power, only electricity in a traditional, for example, system, you can reach an efficiency of 36%, 40%, 45% in the combined system with Rankine and Brayton turbines. This is the higher efficiency you can reach if you produce only power. If you have a cogeneration system, you reach a higher efficiency. Yes, you can reach also 40% of efficiency in electricity, but you can also have a lower efficiency for power. For example, in small plants you can have an efficiency of 20-25%. But you have also the possibility to recover heat, and so you can have another fraction of efficiency for heat production. And so if you consider both power and heat, you can reach efficiencies of 80-90% compared to 40% of a system that produces only power. And this is, of course, the main advantage of cogeneration systems. For the biomass sector, the importance of cogeneration is very probably is higher than in traditional systems, because in the biomass systems the efficiency regarding power part is lower than 40%, 45%. Usually you reach an efficiency of 20%, 20%, 25% for electricity. And so you have 75% of energy in exhaust gas, for example, and is very useful both for environment and for economic case to recover also this thermal energy. A large part of this 75% of thermal energy to, for example, to heat an industrial district, a town, or a commercial quarter, and so on. So it's very important to move toward cogeneration systems. And of course, as I just said to you, the advantages of cogeneration is both for environment, because of course you produce more energy with the same quantity of biofuel. Economical, of course, because yes, you improving the efficiency, you will also improve the economic balance of the system, and of course, energy improves, because improving the efficiency you improve the energy balance. Of course, if you want to have a cogeneration system, you have also to consider this simple thing, but very important, where that you have to, of course, to use electricity and heat. While the electricity, you can also you don't have to use directly electricity, because you can put it into the national grid, and this electricity will be used for another user. But when you consider heat, you have to use heat near the plant, because you can move it in great distances. So you have to use it, and to use it in the same time you produce this heat. And so it's very important to design the plant and to have the plant close to the users that need heat. And these are some some pictures of the cogeneration systems. Of course, you can have diesel engines, and also these are some characteristics of diesel engines, and also turbines. Turbines starting from micro turbines, 100 kilowatt, up to great turbines. And this is the probably a thermodynamic cycle not so common in the traditional systems, because for biomass systems the organic Rankine cycle, ORC, is a very used cycle that is similar to Rankine cycle, but you don't use water. In the Rankine cycle you use water that evaporates and recondensates, and the steam expands in the turbine and produces energy. In the organic Rankine cycle, you use an organic fluid, which is a fluid that can reach at liquid stage very high temperatures. For example, some organic fluids that we use for biomass boilers can reach 300 degrees centigrade at liquid stage. So you can then transfer this high temperature to thermodynamic fluids that gives a very high efficiency to the system. And this is, for example, the organic Rankine cycle in a diagram in temperature and entropy, with the atomic coil at 300, more than 300 degrees centigrade, and of course the final at the end of the process, we of course transfer heat to the water. But with this gap of temperature, you can obtain a great efficiency of the cycle. And this is the energy balance of an organic Rankine turbine that, for example, produce from 18 to 24, 25% of power efficiency, but also a very, very large heat recovery, up to 80%. Of course, it depends on the efficiency of the system, but you can reduce the losses at 2%. So you have 98% of efficiency divided into, of course, into electricity and water recovery, and hot water recovery. Okay? This is, for example, a picture of a system with the organic Rankine cycle turbine and coupled with the biomass boiler. And these are, for example, some efficiency of some turbines available in commerce. For example, this one is a boiler of a little more than 5 megawatt thermal megawatts, okay, that produce 1 megawatt electricity, so a power efficiency of 20%, and recover a very, very large part of the thermal energy, 4.6 megawatt of thermal energy. So the efficiency is very close to 100%. And of course, an evolution of cogeneration is the tree generation. So they combine the production of power, heat, and cooling. Cooling in terms of refrigerated water that you can use for summer conditioning or for the production of refrigerated fluids that you need for some industrial process, for example. And in this way, you have also an high efficiency. Of course, as I said, U is very close to 100% of efficiency. But you can also have the possibility to use it in every part of the year, because you need heat for domestic or for industrial uses only in a part of the year in general. And for example, in summer you need the air conditioning with the cooling system. In this way, you can also use the thermal part of energy in every part of the in every time, in every part of the year. Okay? And of course, if you want to use great quantities of thermal energy, you have to distribute it to a larger quantity of users. And so it's in this industrial plants, it's important to create a district heating, so a pipeline system that distributes heat or refrigerated water to a lot of users, to a small town, to an industrial quarter, a commercial quarter. So you have to reach every user in a space. And so, for example, here you can see the district heating. So here you have the biomass plant where you produce electricity and hot water, and this is the district heating with pipelines that reach every final user. Okay, and in this way you can optimize the distribution of energy, of thermal energy, and the final use of this energy in order to optimize the consumption of energy. These are some examples of district heating, and this pipeline can also reach a length of some kilometers. So nowadays we have some pipes that have as a loss of temperature which is less than 1 degree per kilometer. So if you start from, for example, 90 degrees, if you have 10 kilometers of line, you have still 80 degrees at the final, the last user, which is still a good heat for domestic heating or for yes, conditioning of every space. And this is, for example, a picture of the system with the very important insulation part that avoid losses during a long pathway. And this is, for example, I don't know if you can see, but it's the realization of a district heating in a town, industrial district. And this is the final part of the district heating, where you can see the pipeline coming from the district heating and the part that regards the final user. So you have an heat exchanger here that can connect the district heating to the internal thermal system. Okay? Any question? Okay. Now we can have a look to the second typology of thermal processes, thermal process in biomass, which is gasification. As I said in the previous lesson, gasification is a partial combustion, where you don't give to the system the whole oxygen that needs for complete combustion, but only a part of oxygen. So the effect is that you have, yes, you have a small combustion, but you also have a degradation of biomass, because where you don't have oxygen, the biomass at high temperature transforms it into other products. For example, it has a degradation into syngas. So there is not a complete combustion, but for example, you don't obtain carbon dioxide, but you have a partial combustion and you obtain carbon monoxide, CO, which is still we can also still burn, and we will see how to use it as a fuel. Or, for example, you don't obtain water or evaporated water, but you obtain hydrogen, H2. You obtain, for example, methane, CH4. So you don't have a complete oxidation of each element, and so you obtain some gases that you can burn in another system, because of course the final goal of gasification system is to obtain a gas fuel that you can burn into a turbine. Because of course, if you also in a diesel engine, but the final goal is to obtain a gas fuel that you then can use into another conversion system. Okay, different from the boiler, because if you have a solid biomass, the only way is to burn it into a boiler. If you obtain from this biomass, you obtain a gas biofuel, because it's still renewable fuel. If you obtain a gas biofuel, you can burn it into a turbine or a diesel engine, and you can optimize the efficiency, the power efficiency. So what I will say in words, you can see into this law, where you start from biomass and you obtain syngas, for example, H2, carbon monoxide, CH4, and so this is the syngas. We name it the syngas you can use in a secondary system. Okay. And of course, the part that the partial combustion gives to the system the energy needs for the process. So you need a part of combustion to have energy for the reactions. Of course, we have a partial combustion, so the temperature is lower than traditional combustion system that can reach 1,500 degrees centigrade. We are under 1,000 degrees. These are the final product of syngas, and this is for example, the composition of syngas in function of the system you need for the partial combustion, because you can use directly air, but you can use also only oxygen. So you put away nitrogen and other part of the air. Or you can also use steam, which is used in some gasification system. And of course, the composition of syngas changes, because if you have air, you have a lot of nitrogen in the syngas system, because nitrogen don't contribute to the combustion, and you can find it from air to the syngas in a good part. And then you have, for example, carbon monoxide, which is a fuel, hydrogen, which is a fuel, CH4 or other organic compounds which are still fuels, and of course carbon dioxide, because we have a partial combustion, and also water. If you have oxygen, of course you have a very, very low quantity of nitrogen, and so the percentage of the other elements changes, because you can see that every other part grows up because we don't have nitrogen. And of course the low heating value, which is a characteristic we have seen in the last lesson, is very different. Of course, the low heating value of syngas obtained in air is lower than obtained in oxygen, because of course you have half part of nitrogen which don't contribute to any combustion. And so the difference is quite the double in the two cases. And also you can see also the column of steam, which is a higher low heating value. Why? I just said the reason, but I repeat it. Why we use mainly a gasification process? We use a gasification process if we want to optimize the power production, because if you have a gasification process, you have an efficiency of only gasification of 95%. So starting from biomass, you obtain an efficiency in syngas of 95%. But after, you can use syngas into, as I said, into a turbine, into a diesel engine. And so you can, or also in combined cycles, so Rankine and Brayton cycles. So you can increase power efficiency. For example, 35% for small plants, up to 50% when you have combined cycles. And so an increase in power efficiency, as you should remember that in the organic Rankine cycle systems, you can reach an efficiency maximum of 24%. So here we are from 35% to 50%, so higher efficiencies. And so gasification is a process that is studied for several years just, but is used for increased power efficiency. And of course, you have a lower thermal efficiency, but it depends on what you want to obtain as the primary energy product. And also we have also the purification of syngas, because I've said to you that in syngas we have carbon monoxide, hydrogen, carbon dioxide, water, but you have also a lot of other components that are considered or pollutants, or also a problem, for example, for the turbine. For example, some elements with sulfur can create problems to the turbine. So we have to purify the syngas with the existing existing gas treatment systems to avoid some pollutants or some components which the turbine creating problems or are reach the atmosphere creating a problem of pollution. I can go quickly there because the systems are very similar to the boiler and of course you obtain also a liquid. Also in this case you can obtain a liquid component that you have to treat as a waste, or you have to reuse it as an energy product. But it's very difficult because it's a liquid with a very high density, so it's very difficult to use it as an energy product. And in some cases you have to consider it as a waste. The last process, thermochemical process, is pyrolysis, which is where we don't have anymore any combustion. So it's only a degradation of thermochemical degradation due to a high temperature. We don't have anymore any combustion. So we have high temperature that causes a degradation of biomass. So you transform biomass into three final products, which is a gas product, which we can call heat, for example, syngas, but also pyrogas to have a difference between gasification and pyrolysis final products. You obtain a liquid component, which is tar, and a solid component, which is char. So the pyrolysis transform with the heat, with high temperature, transform biomass into three final products. Of course, you can use pyrogas into a turbine or into an engine, as I said, for the gasification. But you have to also think about how to use these two final products, otherwise they are a waste and it's not so useful in terms of efficiency to consider it as waste. So you can use char, of course, as a solid biofuel, but also you have to think how to use tar in an energy pathway in order to avoid wastes from this process. And there are several typologies of pyrolysis in function of the temperature, from 300 to 500 degrees. The conventional pyrolysis approximately is at 600 degrees. The fast pyrolysis is at this temperature with a very low time of contact. Flash pyrolysis is ever more quick than the fast pyrolysis, very low, and it depends. And slow pyrolysis, we have high temperatures and high time of residence, and every kind of process generate a different ratio between the three final products. So it depends on what you want to obtain mainly in the final products. If you want to obtain gaseous fuel or solid fuel or liquid fuel, you can move between these processes. And here at the table you can see the several processes, the temperature, the speed, in the speed and the residence time, and the final product, the main final product. For example, if you want to obtain gas, you have to go where in the two extreme processes, flash pyrolysis or slow pyrolysis. If you want to obtain liquid, you have to go through this process, and if you want to obtain a similar ratio between the three products, you have the conventional pyrolysis, which is called conventional because yes, you obtain a similar proportion, a similar ratio of the three final products. And of course, you obtain the pyrogas, which has a low heating value between 10 and 25. So there is a large gap between the low heating value that depends on the condition you can obtain. And here some typology. Okay. And this is the table that show the limits for biomass plant of every pollutant in function of the size of the plant. So, for example, you have particulate matter. You have, for example, organic carbon, carbon monoxide, nitrogen oxides, and sulfur oxides. And these are the limits of each pollutant in function of the thermal size of the plant in megawatt. For example, from 150 kilowatts to 3 megawatts, you have these limits. From 3 to 6 megawatts, you have these limits, and so on. And so you have to make a choice of the pollutant treatment systems in function of the results you want to obtain. Respect the Italian normative on emissions in atmosphere. Just a look to the district heating in Europe and in Italy. This is a picture some years ago, which shows the situation of district heating. So we are speaking about every kind of fuel. Probably a lot of these percentages are with methane district heating, but it's a data just to consider in general the sector of district heating. And here you can see that we were approximately at 4% of the sector of residential, in general, heating, while other European countries are more than 30%. For example, Denmark is 60%, Poland 50%, but also, for example, France has double percentage of Italy. Germany is 14%, and so it's a technology and it's a typology of heating which still needs to grow up in Italy. Yes, these data are not so recent, but the district heating is increasing, but not so more. For example, also in our town in Perugia, some years ago, we had a good increasing of district heating. For example, for 5 district heating were realized in Perugia. Of course, these district heating are very small because it's only for a few buildings or a few commercial building or something like that. But it was a good example of district heating. And of course, the fuel is methane, not of course biomass, because it's a very, very more complicated configuration. And for example, San Mariano, which is a quarter very close to here, there is a cogeneration system with 1.5 megawatt of power and 1.6, 1.7 megawatt for thermal use for residential heating. There are, yes, these are some pictures of this district heating. That for in this case regards 150 apartments. So I think there are four buildings fed up by only one boiler system and district heating. Wood chips district heating has more problems than methane district heating, because yes, you have of course have the availability of biomass, and you have also to optimize the pathway, the energy pathway, because if you create a district heating fed up by methane, you don't have think about the fuel, because you have just available your fuel next to the boiler. When you create a biomass wood chips district heating, you have also to coordinate the furniture or the approvisionation of biomass wood chips. There are several biomass district heating in Italy, mainly in the north of Italy, of course, where you have the availability of biomass into the close forest available. But also in the center of Italy there are some examples of biomass district heating. For example, in Tuscany we have free district heating that regards, of course, mountain village, so small town isolated by the main cities, with yes, of course, a good availability of biomass in the neighborhoods. But yes, there are some examples, and it is possible to create this pathway, to create the district heating, the substations, and also evaluate the CO2 not put into the atmosphere, because of course you have, if you have a biomass district heating, you have a double advantages. You have the advantages of every cogeneration system, and so you have the less fuel for more energy, of course. But if you have a renewable fuel, a biofuel, you have also all the advantages of this biomass, and so which is CO2 zero balance biofuel, and so you can save CO2 into atmosphere. For example, this district heating in Cavallese avoid the emission of 24,000 tons CO2 per year. So you have also the advantages of biomass, of the biomass system. Of course, you have to organize the storage, the storage of wood chips, the automatic storage that fill up the boiler, and you have to create area for the realization of the biomass plant, and so it's a little more complicated, but of course possible, and of course you have good economic incentives. You have a good economic balance, both for the property of the biomass, but also for the final users. You have a lot of, you should have an economic save of at least 20% for the final user. So the economics are distributed in all the pathway from the biomass plant to the final user. And these are some pictures of this eating. Here this biomass district in the north of Italy, where of course we have several district heating. I think more than 60 plants only in Alto Adige. And this is one of the first biomass plant with the district heating. The small village is Sondalo, and in 210, but this plant is working since several years before, is a 10 megawatt thermal plant with approximately 20 kilometers of pipelines, 370 final users, so it's probably the whole town is connected to the district heating. It's the second example in the north of Italy is Tirano, which is larger than the Sondalo one, 20 megawatt thermal power and 1.1 power for electricity production, 32 kilometers and 700 final users. And this is some picture of the realization of the district heating, and also the automatic control system for control if some final user have problems, and also control the consumption of each user that pay in function of how much it use energy, and of course they have good economic savings compared to not to methane, because probably in some final users don't have the connection to the methane grid, but you have to compare with, for example, gas oil, with diesel for heating, and the savings, the economic savings are more higher. Probably the savings are more than 50% compared to gas oil heating system. And this is, for example, is an old picture, but you can see a comparison between the price of gas oil for thermal heating and the price of wood chips. You can see that the saving is important, but mainly you don't have the peaks that you have with gas oil, which is an oil product, and so it follows the price of oil, and so we can have some important peaks that you don't have with wood chips. Also, wood chips increase its price in time, but it's more constant than oil price, gas oil price, which is a variability very high. these are some pictures of the storage system, the biomass from forest maintenance or from river maintenance for some agricultural residues and so on. This is the view from a plane from the drone of the area where you can see all the different biomass stored, the wood chips storage, and finally the automatic storage, and of course the boiler and the central for the boiler. Okay. Just the last thing, which is not only for district heating, but is a general consideration of every bioenergy pathway, which is the final use of the final residue of every thermochemical process. We have seen that every thermochemical process obtain energy and produce some residues, some wastes. Some exhausted gas goes into the atmosphere, but you obtain also ashes. In the general view of circular economy, of course, ashes, which are metals, which are the metals every plant, every biomass needs for growing up, should come back to the field. If you can put the ashes into the fields, you close the pathway, and so you can well create a circular economy where you can reduce at the minimum value every waste, every residue of the process. And so this is a general consideration, not only applied to district heating. Okay, now we can move to the second family of bioenergy processes, which are the biological processes. So, in general, a biological process don't need high temperature as in the thermochemical process, because in general we obtain the energy, the process obtain energy not from temperature, from high temperature, but from in general from microorganisms that are the way we obtain energy from these biological processes. The first biological process we have a look is the anaerobic digestion. Anaerobic digestion is a process. Anaerobic means that you are under oxygen, without oxygen, in a condition without oxygen, and yes, we have some microorganisms, bacteria in this case, that transform biomass into simpler product up to the final product, the final bioproduct, which is methane, biomethane in this case, because it is obtained in a renewable way. Of course, we obtain also carbon dioxide, which is typical not only for thermochemical processes but also in biological processes. And so the final product of anaerobic digestion is methane, biogas, which consists mainly of methane and carbon dioxide. Okay. using the terminology we used also into the previous lesson when we talked about the main parameters we use for the biomass description. If we start from an S received biomass, in this kind of biomass we have a very high quantity of water. Of course, the quantity can start from 10 to 98%, but in general we have high quantity of water, 50%, 60%, 70%. Of course, the fraction that is interested into the anaerobic digestion is the solid phase, and of course not ashes, but the part we have named volatile solids, and of course not the undegradable part, but the degradable part, which of course can be used as a food for microorganisms, and it's the complex substances are decomposed into simpler compost in order to obtain energy. So microorganisms use this biomass to break down the diagrams and obtain energy. What are the biomass we can use for the anaerobic digestion? In general, we can use, of course, residues from manure from zootechnical breeding, agro-industrial residues, for example, from milk industry, from beer industry, from wine industry, or of course the degradable part of wastes, but also agricultural residues, for example, straw or other agricultural residues, and of course energy crops. Energy crops are between this biomass the ones that have the higher bioenergy potential, but of course we have to create the correct co-digestion of all this biomass in order to minimize energy costs that requires agricultural fields, and that requires a lot of water, a lot of other nutrients to make the plants grow up. And so we have to start from everything is a residue, and then of course complete with a part of energy crops that gives us the main potential in energy in biogas production. Okay? These are the main energy crops used for anaerobic digestion. Of course, herbaceous biomass, sorghum, maize, and in general cereals. Of course, zootechnical manure, and these are some biogas potential of the biomass we have seen. We can also see it into a table, which is easier to read. And here you can see that, of course, the energy crops that are, for example, maize or other herbaceous crops have a biogas production higher and higher than other residues, and of course manure has a low potential in biogas production, because of course it's a material just digested from animals, and so a lot of the potential in biogas has been used from animals, from cows, from chickens, from animals, and so the potential is lower than energy crops, which is the biomass the animal just hate to take energy to grow up, and the manure is the residue of the energy process of animals. So the difference is this, and also in other agricultural or agro-industrial residues, this one, the potential in biogas is lower. So it's correct to use mainly as possible residues, but of course you need also a part of energy crops, the anaerobic digestion, to reach the decided power of the plant, and so you have to mix this biomass. Okay, how this is the process, the anaerobic digestion process on detail. So, as we have seen, we use only the organic fraction of biomass, not water, not ashes, and so the only organic part of biomass. And what is the composition of this biomass? Of course, we have the main composition of each organic system, so lipids, carbohydrates, and proteins. Of course, these are the three main families we have in every kind of organic fraction of biomass. And so we have several families of bacteria that works in a sequence. So first of all, the hydrolytic bacteria use lipids, carbohydrates, and protein, and they decompose it into simpler substance. For example, carbohydrates are reduced into sugars, into simple sugars. Lipids are reduced into fat acids. Proteins are reduced into amino acids. Then we have another family of bacteria, fermentable bacteria, that decompose it in simpler substance. This one, volatile acids. And then acetogenic bacteria create acetates. And finally, the metagenic bacteria transform acetate into methane and CO2. So the final product is a biogas, which consists of methane and carbon dioxide. And this is our gaseous biofuel that we can use in a turbine or in a diesel engine to produce power, heat, and so on, and make the same consideration we have done for the thermochemical processes. Okay?
Can I ask a question?
Oh, of course.
I heard that the research is trying to stop the process before the last phase, the methanogenesis.
See? Yes.
Trying to obtain hydrogen instead of methane.
See? Yes.
Is it doable, or are they having good results?
Yes. I've shown you a very simplified pathway. Of course, when you have microorganisms, you have more complex reactions. So we are also testing a parallel reaction. We can have, as you say here. So when you have acetate, I should have also a slide here, for example. No, I should have lost the slide. Of course, you can move towards methane or towards hydrogen. Okay, and we also are studying this pathway. But when you work with microorganisms, you have to work with very particular condition of temperature, pH, and so. It's not so easy to move toward another reaction, another final products. But yes, it's a very interesting research topic. So we are not me directly, what my colleagues are working also to this, and they are starting to have interesting results. Okay. You made this question because you work with fuel cells, so you are interested not only to methane but also to hydrogen, and it's a good question because by this way you can obtain a sort of renewable hydrogen, and so you can also jump a lot of problems connected, of course, to fossil fuels and to the not renewable fuels. Yes, it's another interesting research topic.
By the way, the byproduct would be CO2 anyway, right?
Of course, but
it would make the process simpler when it comes to use of the final product. I mean, maybe you could separate directly hydrogen and then avoid I mean, of course, methane could be used inside fuel cells, for example.
Yes,
you would have to
there are a lot of
separate the CO2 at the end of the process.
There are a lot of consideration to add to this discussion because, for example, yes, there are other renewable way to obtain, for example, hydrogen from the electrolysis of water using energy from photovoltaic systems or from ionic system. So there are a lot of consideration, but anyway, it's a good research topics also move towards hydrogen production from anaerobic digestion or microorganisms in general. Yeah. Okay, so these slides are the same things I just said. Yes. Okay. This is the slide I was searching. The acetogenesis that can both moves to acetic acids and then to CH4, but also to H2. So this is the stage. We can we can move towards methane or towards hydrogen production, and yes, this is the one. Otherwise, the final reaction moves to CH4 reception. This is a typical composition of biogas. So, of course, we have the two main products, which are methane and carbon dioxide. And of course, if you have 50% of methane, you have approximately 50% of carbon dioxide. If you are able to reach 80% of methane, of course you have the corresponding value, approximately 20% of carbon dioxide, and a list of other components that in small quantities you can find, for example, nitrogen, and also other compounds that could be a problem, for example, hydrogen, sulfur, or ammonia, which creates some problems if you use biogas into a tube, for example. Of course, the low heating value, the heating value in general, depend on the quantity of methane. So if you have 50% only of methane, the heating value is half than traditional methane. And so we have approximately the methane has a low heating value of 10 kilowatt-hour per cubic meter. So if you have 50% of methane in the syngas, you have 5 kilowatt-hour per cubic meter. If you have 80%, you have 8 kilowatt-hour of cubic meter. And these are the conditions that regulates the anaerobic digestion process. And so you usually choose the temperature, and you can choose a temperature less than 20 degrees centigrade, and so you have a psi profile situation. You can have temperature between 20 and 40, and you have mesophile conditions, and or thermophile condition if you are more than 45 degrees centigrade. And of course, every temperature means a different typology of bacteria that can grow up into the system, and the temperature influences the duration, the time you need for complete the process. Of course, if you have lower temperatures, you have higher time of duration of the process, and of course, if you have higher temperature, you have lower time of duration. In general, we work in mesophile conditions. Usually the temperature is at around 35%, because it's a good compromise between the time of the process and the energy needs to maintain the temperature. Because I can also choose to work at 60 degrees, but work at 60 degrees means that you have to use a lot of heat to maintain this temperature in the digester, and so the costs are higher. So I think 99% of anaerobic digestion systems are in mesophile conditions, and approximately 35 degrees centigrade. Then it's also important the content of solids in biomass, and we can have a wet digestion if the moisture content in biomass is 95%, and so the dry matter is 5-8%. We can have semi-dry conditions if we are between 8 and 20% of dry matter, or we have a dry digestion if we are more than 20% of dry matter. Also here we work very soon in the semi-dry digestion. We can also choose between only one stage or a separated stages, and in general we can work with one only stage reactor where we have hydrolysis, fermentation. Oh, hi.
Can I see?
Yes, of course.
I'm sorry, I missed my train.
No problem.
I know I'm late.
We are just very close to the end of the lesson, but I think that the video of the lesson will be available in the next days, so you can also have a look to the video to have a look to what you have lost. We are speaking about, we have completed the thermochemical processes, so we have just a look to combustion, gasification and pyrolysis processes, and we have just started since 30 minutes I think the biological processes, and in particular we are studying the anaerobic digestion, and so we have looked to the definition of the anaerobic digestion, to the main biomass we can use for this process, and now we can have a look. We are having a look to the parameters that influences the process, and temperature, solid content, separate or unique stage, and the process will be batch. So batch means that you put inside the anaerobic digester a quantity of biomass, you wait some weeks in general, and then you collect, and during the process you collect biogas, and at the end of the process you collect the digested materials that is your residue at the end of the process. You can also work in a continued process, and this is a relative new technology that in the last years has a good development, and where you have a digester where the biomass moves, and you from a side you put inside the biomass, and at the end on the other side you collect the digested material, your residue, and the biogas from the upper part of the plant. Of course there are a lot of other parameters you should know and you should control in this process, because in this process you have microorganisms that works, and so every change of some conditions could create a problem and kill your microorganism, and yes, you have to restart the process and lose a lot of time and of course a lot of money. So you have to control the pH conditions, the concentration of volatile fat acids, also the carbon nitrogen ratio, which is the parameter we have seen in the first slide. We have starting to talk about the bioenergy processes. So a lot of parameters that have to be controlled to guarantee optimal conditions for the microorganism growth and for the, of course, biomass production. So these are the three main conditions, but I just say that in almost all the biogas plant we work in these conditions. So a mesophile condition, which is a good compromise between time of residence of biomass and energy cost to maintain this temperature all the year. And this is the a graphic we use to consider the percentage of growth of bacteria inside the digester in function of time. So you have a rapid increase of bacteria growth and of course of biogas production. You have a peak and then you have a decrease which decelerate a lot, and of course you have to decide when to stop the process, because it's not more convenient to continue the process to produce a very low amount of biogas, but it's preferable to stop the process, to put away the material, the digested material, and restart with new fresh biomass that replicate the rapid increasement of production. And also you can see the different temperature that increase the growth of bacteria and also make them more rapid, because you can see that the peak goes on the left when the temperature increases, and so this is the compromise I told you between times between production and the cost to maintain the temperature. Okay. This is a scheme of a digester, an anaerobic digestion system. Now we had a look only into the anaerobic digester, where the main reactions, where we have the main reaction. But of course, as just done for the thermochemical processes, we have to see all the plant. And so we start from different kind of biomass. We have seen manure, agricultural residues, agro-industrial residues, and of course energy crops, for example maize, sorghum. The digestion system, where you obtain biogas. Normally, biogas is less weight than air, so you collect from the upper part of the digester, and you put biogas into a storage, and then you can use it. You can use it into an engine or a tube to produce electricity and to produce heat. Of course, you can use a fraction of heat for maintaining your temperature condition of 35, 36, 37 degrees, and so every part of the year you need heat. All the heating in the hottest hour of August you don't need to heat the system. In the rest of the year you have to produce hot water, and then you can use the remaining part for everything you want, for heating, domestic heating, or industrial heating if you have a big plant. The digested part, so the material that don't participate to the anaerobic digestion, is separated in solid and liquid phase, but the right use of this digested material is into the field, in order to also just we have told this into the thermochemical processes, but in a view of circular economy, you have to close the chain, you have to close the pathway, putting some elements to the fields that lost these elements for the growth of the plant. So the circular economy is to reduce every kind of waste and transform road waste into a product for another process. And so you obtain compost, fertilizer, and other nutrients for the fields. This is the classic typology of anaerobic digester, which is the batch plant. So you put biomass inside the system, you wait, usually you wait 1 month or 4 weeks to complete the process, and at the end of this process you put away your residue and insert fresh biomass. And this is the more common plant. In the last years, I don't know if you can see, but in the last years, also a continuous plug flow system has been developed, which is a sort of cylinder where you put from a side the biomass. For example, here you put here biomass. You have a movement system that allows biomass moves from the left side to the right side of this picture. And for example, the system is designed in order to have 1 month between the 1 month the biomass goes from here to the end of the system, and the different family of bacteria are distributed into the cylinder, and so we start from the first family of bacteria, then volatile acid bacteria, acidogenic bacteria, and methanogen bacteria at the end of the time. And you can collect biogas from the upper side and the digested material from the lower side. And there is no a law that says you what is the better plan. Of course, the other plant, the batch plant, has a tradition of 50 years. We have the plant from since a lot of years, and this plant has one advantage, which is an environmental advantage. You don't have a 15 meters tall digester, but only a cylinder that is not more than 3 meters tall, is 20 meters length, but only 3 meters tall. So the impact in terms of environmental view is lower, and so this is the reason it has been a good development in the last years. But in terms of efficiency, there is not different. This requires a continuous feeding, so you have you should have an automatic system that take biomass from the storage and put it into the system. In the other batch system, you need one times a month. You have to put away digested and put new materials, and then the systems should work alone. So there is an advantage, but also a disadvantage, which is the continual feeding that could require more controls from operators, from human operators. I propose to don't have another break, so we go for another 20 minutes, and then we finish a little early, but without having a break. If you agree. Otherwise, we have a short break. Want to continue? Okay. So we can call. So I should finish this part. Okay, these are some pictures of the internal part of the anaerobic digester with this movement system. Of course, you also need a movement system inside the digester in order to guarantee the mixing between the bacteria that are moving and the biomass and the food that you are eating. Yeah. And so you have to move also to have an optimal distribution of the other parameters, temperature, pH, and so on. Okay. Before you, when you have collected biogas and before you fed your energy conversion system, turbine or an engine, you have to clean gas that could have some, for example, some solids elements that can create problems to the turbine. You have to reduce the moisture of biogas, which is very wet when it exits from the digester. So you should dry this biogas in order to avoid a condensation into the following condensation that would create some problems. And another important treatment that you have to obtain to your biogas is the elimination of hydrogenated sulfur, because it would also create a problem of corrosion to the tube. And so it's another treatment necessary before use biogas in the tube. And these are some biologic mechanism of desulfuration or chemical processes. I don't repeat what you can produce with the biogas conversion, because it's a thermochemical process. In general, it's a combustion process that or both in diesel or in turbine system can be used to produce power, heat, and also cool water in the view of cogeneration or trigeneration plant. So combine the production of electricity, power, heat, and cool water to satisfy every energy needs you can have for electricity, for air conditioning in winter, for the production of steam, for example, in some industrial process, for the summer cooling, or for the production of refrigerated liquids for industrial purpose. And these are some pictures of diesel or microturbines. The last process we see today, and then I think we can stop for today, because next lesson, I've just said to your colleagues this morning, the course is organized in this way. Today we should conclude the bioenergy processes with the mechanical processes. Then in the next lesson we will see the biofuels and biorefinery sector. So we will see first and second generation bioethanol and biodiesel, and in that lesson we will complete also the bioenergy processes, because, for example, I didn't show you the fermentation process because we will see it applied to the bioethanol production. So we will see the first and second generation bioethanol and biodiesel production, and then we will see all is very important thing. But we'll see a lot of bioproducts you can obtain from biomass. For example, the uses of lignin, the uses of bioplastics, and so on. And this is the next lesson program. In the last lesson, we will go into our laboratories to see what we have just studied. So we will see our instruments, our reactors where we produce bioethanol, we produce nanocrystalline cellulose, and so on. And I have also to find a very not many time to have a final something like an exam, very simple, of course, to evaluate your preparation after this course. So this is the next 2 lessons program. So next lesson is a theory lesson, and the last lesson is a laboratory lesson with the final test, oral test, to evaluate your knowledge. Okay, so we can complete the lesson with mechanical processes. Mechanical processes is a particular family of processes which consider all processes that don't have a thermochemical conversion and don't have a biological process. So, for example, is very used for the extraction, for the production of vegetable oil from seeds. You have a mechanical operation without the use of temperature, so you don't have a thermochemical process. In some cases you reach a very high temperature, but it's not the way you obtain oil, vegetable oil, or in general every process that, for example, transform biomass into wood chips, which is a simple cut into a wood chipper, and it's a mechanical process. Okay. So I don't have many things to say here, because okay, you can start from several kind of crops, and unfortunately here the competition with food crops is very important, because you can see sunflower, soybean, or other crops that are normally used for food, for food or feed also purposes, and so there is no other way to obtain oil. Only, for example, palm oil, coconuts, and so on. The only plant have studied, not only our center but also all over the world, have studied in that it's not a food product, is this plant which is Jatropha. It's a particular plant that grows up into particular climate condition, not in Italy of course, and this plant has interesting production of oil. You can see that it's very similar to palm oil, and of course Jatropha oil is not used for as food. It's not used for food, and so avoid the competition with the traditional agriculture. But of course, it's cultivated only in some countries, and so it's not so diffused as a cultivation. So it's the only alternative to food crops. Otherwise, how can we obtain vegetable oil? And this is the argument of the last lesson, but I can anticipate here because we are speaking about this. How we can obtain vegetable oil from other kind of biomass, from not food biomass. We are working in a very relative new research area, which start from lignocellulosic biomass. So another time we move toward lignocellulosic biomass, which is the more present biomass, and it's not food not for human and not for animals in general. And how can we obtain vegetable oil from biomass, lignocellulosic biomass? We are studying with a particular family of yeast, a particular family of yeast that we call them oleaginous yeast, that has use lignocellulosic material not to produce, for example, bioethanol in a fermentation process, but they transform lignocellulosic biomass into lipids, and they store inside them these lipids, and so we can collect these lipids and of course use it as a vegetable oil, and for example use it for diesel production thanks to the transesterification process we will see next lesson, or use directly vegetable oil for energy purposes, and so for example use it as a biofuel for diesel, a particular diesel engine system. And so this is the alternative to food crops and to food products that we can obtain. Of course, we are studying these processes, of course. The efficiency of the process is very good. So you start from lignocellulosic biomass to obtain lipids. The efficiency is very good. Of course, if you part from the seeds, the 35% of the weight of the seeds is oil. If you part from lignocellulosic material, at the end of the process you can obtain 5, 7, 8% of the initial biomass weight. So we still have to improve the efficiency, but we have also some limits that we cannot overpass. But it's a very promising research topic that has a lower efficiency, but start from residues from lignocellulosic biomass residues, and so we have a less efficiency but more availability of biomass, starting biomass. So it would be interesting to develop it into the next years. So this is the classic mechanical process, which is this one. So you start from seeds. You have a mechanical process that allow to obtain vegetable oil. You can use directly vegetable oil in a diesel engine, for example, to produce power and heat, or you can go to a transesterification process. We will see in detail next lesson this process to obtain biodiesel in substitution of diesel for transport sector. You have only a residue here, which is the we name it panel, which can be used in a lot of seeds. The panel, the obtained panel, can be used for food, for feed in zootechnical sector. I show you jatropha as a substitute to food crops. Another very promising crop for using vegetable oil from not food crop is cardoon. Cardoon is a plant that we are studying in the last not more than 10 years. Is a crop that grows up without water. Of course, without water you have to put to the system, but it can grow up only with rain, and also in a region where rain is very low, and has a very interesting production of seeds and of lignocellulosic matter. So it's very promising. Also, this I will show you probably in the next lesson, and also in the laboratory where we work every day with carbon seeds and carbon energy pathway. And so cardoon is a crops that don't requires traditional agricultural fields, because you can also cultivate cardoon into marginal lands, and so there is no competition with food fields. It's not a food material, and so you don't obtain a product in competition with agricultural food, and requires very low treatment and very low quantity of water. So a lot of good information that should allow the diffusion of cardoon crops in a lot of countries. And you obtain from 1 hectare of marginal land with very low water, very low treatments, you obtain approximately 15 tons of lignocellulosic material, and half ton, so 500 kilograms of oil, which is not so much, but you have to consider that you are in a marginal land, you don't use water, and you have a lot of lignocellulosic material that you can also use for example, for oleaginous yeast. And also, if you have less than 10% of efficiency, you obtain another quantity of oil to add to your energy pathway. So it's a very promising crop, and we will speak about this crop more in the last lessons. This is the efficiency you obtain in mechanical treatment, but of course it depends on the quantity of oil you have in the seed. So it's not an efficiency of the process, it's an efficiency that is proportional to the quantity of the oil in the seeds, which is more or less, for example, in this case, could be 38–40%. You can collect 33%, and the remaining part, 3, 4, 5% is under the panel. This is a physical treatment. You can also use a chemical treatment, but for example, in Italy, it's not allowed if you want to produce energy from oil. So you can't use a chemical extraction from, for example, using esano, I don't know, esan product, chemical product to extract with the chemical process. But you can use this process if you want to produce bioenergy. So you can only use a mechanical process. But for example, in Italy we can use chemical extraction for extracting oil for food. So it's very strange. You can use chemical process for produce energy, but you can use chemical extraction for food oil. Okay, these are some processes, but if you use oil for energy purposes, you can stop to filtration. So yes, it's correct to filtrate oil, but you can stop here. The other processes, centrifugation, raffination, and so on, is only for alimental oil. If you use directly vegetable oil into an engine, you have to consider, and then we can stop here, you have to consider the difference between the chemical composition of, this is approximately the composition of diesel, okay, which is a chain of 16 carbon atoms, and of course the corresponding hydrogen, while the chemical structure of vegetable oil is around 57 carbons. So the very important difference is the density. Vegetable oil has a higher density than diesel, and so this is the problem. All the problems are connected with this difference of density, because you have problems in the injection system and so on, and you should, for example, you should preheat vegetable oil to reduce density. For example, this is the difference between the density of diesel and the density of different vegetable oils coming from sunflower, palm, and so on. And the way you can improve, you can reduce the problems of using vegetable oil in engine is to increase the temperature. So this is the density or the viscosity, better, the viscosity of diesel in function of temperature. So normally you have a viscosity between 4 or 5 centistokes. And at 20 degrees you have a viscosity for vegetable oil very high, 70 centistokes. So the only way is to preheat vegetable oil up to 80 degrees in order to reduce the viscosity to less than 10 centistokes and to stay very close to the viscosity of the diesel. But it's a very high cost in terms of energy, in terms of money, and so it's not so used directly into engines. Of course, I'm not speaking about the transport sector, but I'm speaking about engines to produce power. So a static engine that produces power and heat in a generation system. But it's not so used, and so the reason that in many cases we have another process, which is the transesterification, in order to transform vegetable oil into biodiesel. And when you have biodiesel, you have a very, very similar condition to the parameters, very similar to the traditional diesel, and so you can use it into the cars for transport sector. Okay. Any question? Okay. I think we can stop here.